Okay, let's do something actually legit fun. Cover of book. Once again, the cover of the textbook appears. So, I have a matrix A, which we shall say is n by m. That makes this left space what? Good. Left space is the domain. And the domain in this case is Rm as a vector space. What does that make the space over there?
Rn in the codomain.
That makes it the codomain, or the target sometimes it's called. Rn. Okay. Which spaces do we know already? Oh, we accidentally discovered right angle here last time. And what are these two spaces?
Row, null.
Okay. The row space of A and the null space of A. Which space do I know about over there?
The column.
The column space of A, and which one is it? How do I know it's the top right? Because that's when we wrote where we wrote it last time. Good. Also, because the number of linearly independent rows is the number of linearly independent columns, and so the row space and the column space are the same size because they're the same dimension. You guys see that?
Yeah.
So the dimensions of these guys, I'm going to write maybe, so the dimension of the row space of A is, I don't know, it's the rank of the matrix, right?
Oh yeah, that's a thing.
You guys with me on that? And that is the same size as this column space. So the dimension of the column space of A is the rank of our matrix A. Okay, there was another fact called the Counting Theorem that said that the size of the domain, right, M, is equal to what?
Is R equal to R?
The dimension of the null space of A is one.
Good. The size of the domain, right? The whole domain is pictured here.
Yeah.
This part is rank sized, so this part is whatever's left sized. You guys see that? So the dimension of this guy is M minus R. So I'm going to adjust my labeling here. So this is the null space, and the dimension of the null space is M minus rank of A.
Oh. Yeah.
Right. So Rm is made out of these two pieces, and we know they're perpendicular, and they meet at the zero vector. We discovered that by accident. Okay, now, tell me about the row space, but tell me about the row space in terms of something else. That's the vaguest question. Okay. How about, I've got an n by m matrix that goes that way, right?
Yeah.
How big would a matrix coming this way have to be? It would have to be an m by n matrix. And what is the m by n matrix that you always know you can make out of a matrix A? Perfect. You can always make the transpose matrix. So don't get attached to the idea that matrix go that way, inverse matrix go this way, because there's not generally an inverse matrix, right? So the matrix I know I can make is going to be the transpose. Now, what about the row space in terms of the transpose matrix?
Row space in terms of the transpose matrix?
Yeah, so tell me about the rows of A in terms of something of A transpose.
Rows of A are the columns.
Oh shit, you guys are really on that. Okay, so the rows of A are the columns of A transpose, right? So the row space of A is also the column space of A transpose. You guys see that? Self-same space. Okay. What do you want to guess that makes this?
Is that going to be the null space of A transpose?
It damn well better be, because the column space of A is the row space of A transpose. Right?
Right.
And so this thing has one and only one choice, it's the null space of A transpose. You guys see this? And keep in mind, right, the rank of A and the rank of A transpose are the same. You guys see that?
Null space of A transpose and null space of A is
Close. So, it means that I can apply the counting theorem to both sides, right? So over here the counting theorem says that nullity, oops, that's in the wrong color. Over here on the left, right, the counting theorem says nullity plus rank is m, right, which I used to say the dimension of the null space is m minus the rank of A.
Oh, so that would be N minus the rank of
Yeah, and over here on the right, the same thing's true, but it's true for the other matrix. So over here, nullity, and again over here I'm talking about A transposes nullity, plus the rank, and over here I'm talking about the rank of A transpose, but they're the same. And this has to equal n. So if the matrix is square, yeah, they have to be the same size. But if the matrix isn't square, then one of them could be bigger or smaller. Does that make sense? Just with me on that? So the dimension of the null space of A transpose is n minus rank of A. Really should be A transpose, but the rank of A and A transpose are the same. How do I know they're the same? Because the number of linearly independent rows is the number of linearly independent columns. Can you see that? So, this is almost all of the picture on the front of the book explained. Not quite all of. There's one little thing that we need to talk about, but this is pretty much the gist of it. You guys cool with that? So, the thing I want you to do is an example, and I want you to take a matrix and find all four subspaces. So find dimensions and bases. Bases. I never know how to plural that word. Basis plural.
Bases.
Based. Bases. Basod.
No, it's
Bases.
I like bases. Not ba- It is
I'm gonna
bases.
go with basises, but whatever. Of the four subspaces. So I'm going to say the phrase four subspaces a lot coming up. They're these four subspaces. Right? Four. And here's your little matrix. 1, 2, 4, 2, 4, 8. And I'm going to call this one A. You guys good with this? So, ready, set, go.
A. Okay, so
So, augmented. Good advice.